So we're working with what are called growth models, and sometimes things grow in a negative way, and that's called decay or depreciation kind of thing. So things will go up, things will go down. The main types of growth models that we're working with here are called linear. So that's the first type. And in your past life in math, you probably graphed lots of straight lines and looked at story problems. Linear type things, you might remember equations like y equals mx plus b, where m is our slope. Nope. We have rise over run. And then b is called the y-intercept. And we're going to pick these apart some more. Switch colors there. Just a reminder. So y-intercept is whatever y value we're calling that b here. You hit the axis at, and the slope from any point to any other point is your rise and your run. We'll play with that idea a little bit more. Now, sometimes things are more points than connected lines. So there's a type of a linear equation we'll work with called a recursive equation. And recursive is just kind of like making a table of values where you have some kind of a period. We usually call the period counter n, and then you have some maybe population, I'll call that p. And we'll usually start counting at 0, some starting point, and then 1, 2, 3. And sometimes the 0 throws people that we start counting at 0. But if you think about it in terms of like age, a friend of mine had a baby last month. How old is that baby? Well, it's not 1 yet. We don't call somebody 1 until they've been alive for a whole year. So right now they're kind of in their 0 year, but it is their first year. So when we talk about age, the first year you're not 1 yet, and in the second year you're not 2 yet. It's not till the end of the year that we start counting that. So having a 0 period or a 0 starting point turns out is important, and we're going to keep track of it here. And that 0 is a lot like our b over here, that starting point for the counter. So maybe something starts at 1, and maybe that could be 1 million or 1,000, or maybe just one individual, and then it goes from there. So maybe I'll have 1, 3, 5, 7. So in terms of a recursive pattern here, I would just say this starts at 1. And then adds 2 repeatedly. And the notation for that would look something like P0 equals 1, Pn equals Pn minus 1 plus 2. So the first equation says, hey, start at 1. The second equation says n is any place, like maybe n could be 3. N minus 1 would be whatever the previous pointer is. And it just says, hey, add 2 to get the next number, as all this equation here says. So sometimes we look at what are called recursive equations, and we'll see those in a couple of different contexts. And for linear, a recursive equation is either going to add or connection between these recursive equations to the linear equation above there, that's called an explicit equation. And the connection for the explicit equation here is if you repeatedly add, that's multiplication. So that repeated addition is going to turn into a multiplication by what? Well, by my counter. I'm counting maybe months here. So I would take 2 times however many months went by, plus whatever my starting point is. So that repeated addition is basically, in this case, your slope. Again, this type of equation is called an explicit equation. With the recursive one, if I said, hey, find me the 100th, what's going on in the 100th month? Well, one at a time, you have to add 2 over and over and over again, and that's kind of tedious. So the shortcut for the explicit equation is kind of nice, because it immediately gets us to that 100th position if we need it. And good morning, Alexis. Good morning, Lucilla. Again, we'll dive into this in more detail in a minute. So big ideas here. First big topic is linear. Linear equations will either be recursive or explicit. And we just have to kind of sort out which we're going to use and why. Recursive one is great for a spreadsheet. Next big type of thing we're going to deal with in this section are exponential or geometric situations. So if something's referred to as a geometric situation, that's the same thing as being exponential. And there's 2 ways to think about these right here. So we have a recursive way. And a recursive way is multiplication. So you have to start somewhere. And then instead of like the linear, we add repeatedly. In this case, we would multiply repeatedly. And with either the recursive or the explicit one we'll get to in a minute, the multiplier here, that multiply repeatedly, that is called our growth factor. Factor is just something you multiply by. So like maybe think about an interest rate. I wish I had a savings account that paid 10%. Good luck finding one of those. That would be 0.1, 1/10 as a decimal. So it could be that I start with $100, and then that's going to grow by 10%. If that grows by 10%, then what's going to happen is starting with that 100, I'm going to add on to that 100 times 10%, which is going to give me $100 plus $10 or $110. We looked at in the problem solving section, taking a new amount and dividing by the old amount. So my new amount is the 110. So if I think about relative or percent change, if I take the new amount and divide by the old amount, so in this case, that would be the 110 divided by the 100, that's going to give me 1.1, which is 110%. That's the way I can think about that. And this taking the percent and adding it to the original amount gives us what we call a growth multiplier. Not the growth factor, but the growth multiplier. And the growth multiplier is always going to be 1 plus whatever R was as a decimal. By 110% here. And that's nice because adding 1 is pretty easy. And then I can very quickly get the next number. So to get the next number here in my list, I'm just going to multiply by 110% or 1.1. That's going to give me my $110. And then we just keep repeating that process over and over again. My account's increasing by 10%. That means I'll have 110% of what I had before. That in this case is going to be 121. Better calculator out soon. Help me out here. Now, if I recognize that a growth factor leads to a growth multiplier, that leads me to the explicit equation. Because at this point here, if somebody says, well, what's going to happen in 30 years? I get to repeat this process 30 times. Easy on a spreadsheet, pain on a calculator. Repeated multiplication, that's an exponent, right? So then the explicit formula comes from the growth multiplier. Explicit. And so that would be take whatever the starting amount is, usually we call that P with a 0, and multiply it by 1 plus R, however many times you need. And years later, and months later, and days later, whatever it ends up being. So we take that repeated multiplication, turn it into an exponent. The base is always going to be 1 plus R. Look at a bunch of variations of that. And then the third big topic, again, we'll come back to all of this, different problems. Is the idea of solving for exponents. In previous math classes, you probably are really good at solving equations by adding and subtracting and multiplying and dividing by numbers to get things to work out. But if something is in the power position, like suppose I had something like 10 to some power was equal to 75, what power could that be? Well, like backtracking a little bit, I know 10 to the first is 10, and I know 10 to the second is 100. So that power is going to be somewhere between 1 and 2. What is the power? How do we solve for n here? And it turns out the only way to solve for n is with a logarithm. And if you look up logarithm in a dictionary, it's going to say a logarithm is the exponent you need to get a certain result. So a logarithm is an exponent. So to solve something like this, there's two ways to do it. I'll just mention the first way based on the definition of what logarithm means is the logarithm is the exponent. Well, what's my exponent here? Well, it's n. I don't know what n is, but I know n is equals a logarithm. I'm going to abbreviate log. Now, if I have an exponent, I have to have the base, and we write the base as a subscript to the word log, like that. And then the answer I want to get goes in parentheses next to it. So I'm going to whip out a calculator. Calculators have log buttons on them. Get Desmos out here. And let's see, I don't see it on that screen. So I'm going to go over here to functions. They have an LOG here. Now they're not writing a base. If the base isn't present, the base has to be assumed to be 10. That works on 90% of calculators in the world. There are some calculators where if the base is assumed to be another weird number called E, which is like pi, we'll get to that later. But this log right there should be log base 10, just to check, like what power of 10 gives me 100? It would be the second power. right? Logarithm just spits out the exponent to go with your base. No base written means the base is assumed to be 10. Okay, so just checking to see if it does what I think it should. So now if I say, what power do I need to get 75 from a base of 10? It's going to say about 1.875. And I can check that by just saying, okay, what is 10 raised to the power 1.875? And since I'm rounding that number, I'm not going to get exactly 75, but I'll get close to 75. The more decimal places I add there, like what's next, a 0, 6, 1, 2, right? I'm getting closer as I add decimals, 6, 3. And so Desmos must be storing more decimals than it's showing me here because I still don't have the exact answer. But with logarithms, we almost never get an exact answer. It's always approximate to however many decimal places we decide to stop at. All right, what's that number again? It was about I'm going to go 1.875. Approximately 1.875. So that tells me that 10 to the power 1.875 is about close enough 75. And again, I use wavy equals anytime I'm rounding. So if somebody says, well, what's the exact answer? Well, unfortunately, the only way I can get an exact answer is to leave it like this and not plug it into the calculator. Once I plug it in the calculator, it's approximate. So this is the only exact answer to this problem. It's a little messy looking, but life is messy. So we'll go over some more tricks for finding these exponents, but the bottom line is anytime you're looking for a missing exponent, you have to figure out how to use a logarithm to get it. So we'll puzzle with that a little later too. And the last big main topic here, that button, is what's called logistic growth. Logistic. So far, we've looked at the idea of linear growth, something going up in a straight line. Exponential growth usually looks like a hockey stick kind of curve, but exponential growth, it starts off shallow, but then it gets steep fast. Once it starts to climb, it climbs. So this would be exponential. Exponential. But things can't grow forever. It's just not possible. There's finite resources. So logistic growth kind of finds a balance for that. So it looks at things that start off exponential, but then all of a sudden things start to slow down and level out. So it has like an S-type curve. So this is logistic, has this shape. Logistic equations are much more complicated to get that tipping point where things start to slow down here. And so the formula for the logistic, we're going to do it recursively. The explicit one's a bit more complicated, and even the recursive is a bit complicated. So population at some time n is going to be equal to the previous population plus our growth rate. So if I just stopped here, multiplying by the Pn-1, that would be exponential growth, right? Exponential growth says, hey, you just get to tack on a % increase at the end. So what logistic does is it adds a multiple onto this part right here, where it takes 1 minus whatever the previous population was, divided by some number called k. And k is called the carrying capacity. And the carrying capacity, I'm gonna put that in red here, K, that's where the graph levels off. It's like you've exceeded your resources, you can't grow anymore kind of thing. Like if you put bacteria in a dish and let them grow, give them as much food as they want, they're eventually gonna start dying off at the same rate they're growing, leveling off at some capacity that that dish can handle. Same thing with, say, deer in a population or rabbits, wolves, whatever, there's going to be some limit as to what the region can handle. And that's what the carrying capacity K is about. And again, this is the recursive version of that, which we'll work out on a spreadsheet or a calculator. Now, often what happens in reality with these is it's not quite as nice as this. And I know you might look at this equation and think that equation ain't nice. That's complicated. It is, but if we're careful, we can work it out. What often happens in reality, if this is the carrying capacity here, some population has lots of resources, it starts growing quickly, and the population doesn't know there's a carrying capacity, right? It's just going to grow as long as it can, but all of a sudden it realizes, oh my gosh, we're running out of food, or there's too many together and disease starts to spread. They exceed the carrying capacity and then they drop. Once they're under it again, resources become more abundant, space is more open, and they kind of cycle around it over time. So that's more often what happens in populations, that once they reach their limit, they just kind of bounce up and down around it from period to period. We will not get to equations that look like that. All right, that's it. 4 main topics. We got linear growth, exponential growth, solving for exponents, and logistic growth. Now we just need to get used to working with these things. And some of it should be review besides logistic growth.